In this example, we will apply the conservation of mass principle to a large tank that is being filled. The tank has a small leak, allowing some of the fluid that has entered the system to leak out. Let's start by drawing a schematic of our system. We have a tank with a hole in it and a faucet that will be used to fill the tank. We label the flow station from the faucet into the tank as Station 1 and the small leak hole in the tank as Station 2. Now let's collect what we know from the problem statement. We are told that the fluid is water with a constant density of 1,000 kilograms per meter cubed. The flow area of the faucet is 0.1 meters squared, and the area of the leak is 0.01 meters squared. The flow velocity from the faucet to the tank is 10 meters per second, and the flow velocity through the leak is 0.1 meters per second. For a tank that starts out completely empty, let's find the mass of water in the tank after 5 minutes. The first step to solving any thermodynamic problem is to define the system. Returning to the schematic, we draw the boundary for the system around the internal volume of the tank. This control volume represents an open system in which mass is entering through Station 1 and leaving through Station 2. Now, we apply the conservation of mass principle by writing a mass balance for the system. The rate of change of mass within the control volume is equal to the sum of mass flow rates into the system minus the sum of mass flow rates out of the system. For this single inlet, single exit system, the result is that the time rate of change of mass contained in the control volume is equal to the mass flow rate at Station 1 minus the mass flow rate at Station 2. Next, we can evaluate the mass flow rate. For a one-dimensional flow, the mass flow rate is equal to the density times the velocity times the area. Substituting this into the mass balance for Station 1 and Station 2, we see that the rate of change of mass within the system is equal to the density times the velocity times the area at Station 1 minus the density times the velocity times the area at Station 2. By inspection, we see that the right-hand side of this mass balance is constant in time. For convenience, let's define a constant to represent this expression. Let's call it C. This C is simply for convenience and has nothing to do with specific heats or any other property that we typically represent with a C. Rewriting the mass balance in terms of C, we see that the rate of change of mass within the system is equal to a constant, which we called C. We can separate and integrate this expression. The differential mass in the system is equal to our constant times the differential time. Integrating both sides from time 1 to time 2, we see that the mass at time 2 minus the mass at time 1 is equal to our constant times the change in time. Notice that the constant pulls out of the integral. Finally, we substitute the right-hand side of the mass balance for C and see that the final mass minus the initial mass is equal to the density times velocity times area at Station 1 minus the density times velocity times area at Station 2, all times the time interval. Substituting values, we see that the final mass minus 0 is equal to 1,000 kilograms per meter cubed times 10 meters per second times 0.1 meters squared minus 1,000 kilograms per meter cubed times 0.1 meters per second times 0.1 meters squared. All of this times 5 minutes. We convert the minutes into seconds using 60 seconds per minute. The result is that the final mass of water in the tank is about 3 million kilograms. This must be a pretty large tank, and we see that a flow of 10 meters per second through an area of 0.1 meters squared is a very large flow rate for water. As an exercise, you can ask yourself the following questions. First, how much water leaked out of the tank during the 5 minutes? The answer is 300 kilograms. Second, if the faucet is turned off, how long will it take for the tank to completely empty? The answer is about 832 hours, or 35 days. That concludes the example. Thanks for tuning in, and have a great day.